Hello, this is part D of the Chapter 7 lesson. In this part we're going to introduce our fourth type of hypothesis test. In this hypothesis test we're going to be comparing means from two independent populations. So to illustrate this, let's look at example 7.8 from the textbook. And in this example we're asked the question, is there a statistically significant difference in the mean systolic blood pressures between men and women? So we want to compare the blood pressures of men to the blood pressures of women, and specifically we want to compare the mean blood pressure of men to the mean blood pressure of women and ask, is there a difference? So the claim or the research hypothesis that we're going to make is that the means are not equal. Now we're not claiming that that men's is higher than women's or that women's is higher than men or something like that. We're just claiming that they're not equal. So let's make an observation. We have two independent populations, all men and all women. And so men form one population, women form another population. And they're independent in the sense that what happens to one population in terms of blood pressure has no effect on what happens to the other population. And we are comparing the means of these two populations. So again, we have two independent populations. We're comparing the mean of the first population to the mean of the second population. That's what we're doing in this type of test. Okay. So the first step in any hypothesis test is to define the parameters. And so we're going to have two of them, mu1 and mu2. Mu1 is going to be the mean of the first population, mu2 the mean of the second. So specifically, mu1 is the mean systolic blood pressure of all men. Mu2 is the mean blood pressure of all women. Again, we include these words all here to stress the fact that we're making a claim about these two populations, not just the few people in a sample. Now the next step is to set up our hypotheses, and as always the null hypothesis is going to be the general statement that there is no difference or there is no change. So if there is no difference between these two populations, then mu1 would equal mu2. And so our null hypothesis in mathematical notation will be the statement that mu1 equals mu2. Okay. Now to get our alternative hypothesis, we'll go back and look at the claim. The claim is that mu1 is not equal to mu2. And so in the mathematical notation, the alternative hypothesis is the statement that mu1 is not equal to mu2. And so this is our alternative hypothesis, so we're going to have a two-tailed test. Now equivalent way of stating our hypotheses is H0 is that there is not a difference between the population means, and H1 is that there is a difference. So no difference versus there is a difference. Now, as always, to determine with 100% certainty if our claim were true or false, we'd have to go out and survey all members of both populations. So that means we'd have to go out and take the blood pressures of all men and the blood pressures of all women and calculate the population means and compare them. Well, that's impossible to do. So instead we're going to get data from samples. And so what we did is we went out and we surveyed 1,623 men, took each of their blood pressures. The mean of those blood pressures was 128.2, and they had a standard deviation of 17.5. Likewise, we measured the blood pressures of 1,911 women. They had a mean of 126.5 and a standard deviation of 20.1. So if we compare these two sample means, we note that they're not identical. There is a little bit of difference between them. So that appears to support our claim. But remember that this number here is an estimate of mu1. This number here is an estimate of mu2. So just because these numbers are different doesn't mean for certain that mu1 and mu2 are different. So the data appear to support the claim, but we want to ask just how strong is that support. And a hypothesis test is going to allow us to do that. So the hypothesis test that we're going to do here is called the two-sample z-test. The book talks about two different tests, the z-test and the t-test. We'll talk about the difference between them here in a bit, but in this case it's the z-test. And so if we go to the workbook chapter 7 and the worksheet difference of means. We're going to see some yellow and green cells. As always, we can enter things in the yellow cells, and the green things are automatically calculated. And so in these cells here, we're going to enter our sample statistics. So here N1 is the number, the sample size from our first sample, which in this case is men, and then X bar 1, that's the mean from the first sample. S1 is the standard deviation from the first sample. And then in these cells here, we enter the statistics from our second sample. And then down here is the number of tails. This is a two-tailed test because our alternative hypothesis has a not equal to sign. Down here we calculate what the book calls the pooled standard deviation, denoted SP. Over here is our test statistic, and then here's our p-value. Now we're going to interpret that p-value just like every other p-value. Compare that to alpha, 0.05, our significance level. In this case, the p-value is less than alpha, and so our conclusion is that we reject the null hypothesis in favor of the alternative hypothesis. So we reject the statement of no difference in favor of the statement that there is a difference. And so in kind of more informal terms, we would say that there is a statistically significant difference in the mean blood pressure between men and women. So our data appeared to support the claim, and our hypothesis test tells us that there is enough strength to indeed support the claim. Now let's talk about these types of tests that we do in this section. We have two of them, the two-sample Z or the two-sample T test. The purpose of both of them is to test a claim about the mean of two independent populations. And the key word here is independent. Independent means that what happens to one population has no effect on the other population. In our next lesson, we'll talk about a situation where we have dependent populations, where one affects the value of the other. And we're going to have to do something different in those cases. But to kind of summarize what the book talks about is that if to determine what type of test we have all depends on our sample sizes. If both of our sample sizes are bigger than 30, then we use the Z test. If both of our samples are less than 30, then we would use the T test. And the Excel worksheet is set up to automatically determine which test we use, and so it takes care of all that, so we don't have to worry about that. Requirements for this type of test is number one, the samples are random. That's always a requirement. Number two, the samples are independent. Again, this word independent is very important. Number three, the two populations have the same standard deviation. And the book talks about how to determine that, how to check if that's met or not. And then the fourth, either the populations are normally distributed or both sample sizes are bigger than 30. And again, we've seen this requirement of populations being normally distributed come up before. Whenever we make a claim about a population mean, we need to have either normally distributed or a large sample size. That's a fact that we're going to talk more about in Chapter 10. So let's look at another example. This is example 7.9 from the textbook. To test a new cholesterol-lowering drug, some patients are put on the drug and some are put on a placebo, and their cholesterols are measured 6 weeks later. So we got one group of people that we put on the drug, another group of people that we put on the placebo, and we're going to compare these two groups of people 6 weeks later. So the question that we want to ask is, does the new drug significantly lower cholesterol? Or stated another way, does the drug really work better than a placebo? So the claim or the research hypothesis that we're going to test is that the drug does indeed lower cholesterol. So specifically, what we're going to test is that the claim that the mean cholesterol for those on the drug is lower than the mean cholesterol for those on the placebo. So we're going to be comparing population means just like we did in the first example. So as in the first example, we're comparing two independent populations. The first is all patients on the drug, and then number two, all patients on the placebo. Again, we're interested in all patients on the drug and all patients on the placebo, not just the few in our sample that we'll talk about. So our parameters, mu1 and mu2. Mu1 is the mean of the first population, so the mean cholesterol of all patients on the drug. Mu2 is the mean of the second population, so the mean cholesterol of all patients on the placebo. So now we need to set up our hypotheses. The null hypothesis is the statement that there is no difference. So if there's no difference, then mu1 would equal mu2. So our null hypothesis is the statement that mu1 equals mu2. Now to get our alternative, we go back to our claim, which is that mu1 is less than mu2. And so our alternative is the statement that mu1 is less than mu2. So we see we have a left-tailed test or a one-tailed test in general. So an equivalent way of stating our hypotheses is that the null is that the drug is not effective, and the alternative is that the new drug is effective. So to test our claim, we went out, we gave the drug to 15 patients. We took their cholesterol 6 weeks later, and they had a mean of 195.9, and their standard deviation was 28.7. We put 15 people on a placebo. Their cholesterol 6 weeks later were 227, with a standard deviation of 30.3. So notice that this mean is indeed lower than this mean here. So that's an indication that our drug is effective. But as always, we need to remember that this number is an estimate of mu1. This number is an estimate of mu2. Just because this estimate is lower than this estimate doesn't mean for certain that mu1 is less than mu2. So in this case, we're going to be using the two-sample t-test. That's because both of our samples are rather small. And so here's our data. Here are our hypotheses. We enter our data into the yellow cells. We have a one-tailed test. Here's our test statistic. Here's our p-value. Interpret that p-value as before. That p-value is less than 0.05. And so we would reject the null hypothesis in favor of the alternative. So in other words, the new drug appears to be effective. So our data appeared to support the claim, and our hypothesis test tells us that the strength of the support is indeed high enough to conclude that the data support the claim.